Artem Kravchuk, and the talk is about spectral properties of the transposition graph.
Okay, can I start?
Oh yeah, sure, please.
Okay, so in this talk, we'll study the spectrum of transposition network Gaussian graph. And to begin with, I'll give you a few definitions and tell you about the properties of this graph. Then I'll give you a sketch of proof of the theorem that was proved by me and Konstantinova Elena Valentinovna a couple of months ago. And then I'll give you a sketch of proof of the theorems about the third and fourth largest eigenvalues of transposition graph which was proved a couple of months ago too. Okay, let's start. Definition: the transposition graph Dn is defined as scalar graph over the symmetric group sim-sub generated by all transpositions. Here you can see the example. It's T3 graph and G is symmetric group sim-sub3, and the generating set is presented by all transpositions from the set of 1, 2 to 3 and 1, 3. And how we draw the edges? We take element of group, for example, 1 to 3, and we multiply 1 to 3 by some element from generating set 1, 2, and it's equal to 2 and 3, and we draw this edge. Then we take 1 to 3 multiply by 2, 3, and it's equal to 1, 3, 2, and then we draw this edge, and so on for all edges. And here you can see the properties of some properties of transposition network graph. It's connected graph because we can get from one element of group any other element of the group by multiplying it by transpositions, by finite number of transpositions. This graph is connected because multiplication by transposition changes the parity, and it's combination of n by 2 regular because cardinality of generating of transposition set is combination of n by 2, and order of this graph is n factorial because we have n factorial permutations, and this graph is integral. It means that its spectrum consists of integers. Okay, next. We need to define partition. Partition of n is sequence n1 so on to nk, such that n1 greater than or equal to n2 and so on to nk, and sum of this sequence is equal to n. And now we will formulate a theorem that's very important for today's talk, and proof of this theorem can be found here. So let I be a partition of n, then lambda I, which is equal to this expression, then lambda I is an element of the spectrum of transposition network graph. Thus, we can put a correspondence between some partition and the eigenvalue. But looking at this expression, it's difficult to understand. It's difficult to understand, for example, is 0 is an element of spectrum, or is 1 is element of the spectrum, and so on for all integer numbers. And today we will try to study which integer numbers lie in spectrum of the transposition network graph. And now we will formulate and provide sketch of proof of the result that was recently obtained by me and Konstantinova Elena Valentinovna. this theorem that for any integer k at least 0, there exists in 0, such that for any n at least in 0 and any m integer m from 0 to k, m is an element of the spectrum of transposition of Tn. It means that for any big N, we have some upper bound such that numbers 0, 1, 2, and so on to some upper bound will be elements of the spectrum. And since transposition graph is bipartite, then if any integer number I lies in spectrum, then number minus I will be lie in spectrum too. And n multiplied by n minus 1 divide 2 is the largest element, is the largest eigenvalue of transposition network graph, and we will show this fact later. But here, from some upper bound to the largest eigenvalue, we don't know which numbers are eigenvalues of transposition network graph. So let's prove this theorem. But before proving this theorem, we need to prove some technical lemmas. Lemma 1 is about eigenvalue 0, that for any odd n at least 1, the next partition corresponds to the eigenvalue 0 of transposition graph. The partition is n plus 1 over 2, and 1 repeats n minus 1 over 2 times. And for any even n at least 4, the next partition corresponds to the eigenvalue 0 of transposition graph. So we can take from this lemma that if we choose some big n, then 0 will be eigenvalue will be lies in spectrum of Tn, n at least 4. Okay, let's prove, and we prove this lemma by direct substitution of these two partitions into the expression 1. Expression 1 is about correspondence between partition and eigenvalue. Okay, and so we substitute partition for odd case into the expression 1, and after the reduction of such terms, the expression is reduced to 0. And next, we will consider even case. If n is even, then we substitute partition for even case into the expression 1, 2. And after the reduction of such terms, this expression is reduced to 0, 2. And now we need to note that that this partition for odd case holds for any odd n at least 1. Because n plus 1 over 2 is greater than is greater than or equal to 1 if and only if n at least 1. And this partition for even case holds for any even n at least 4, because n over 2 greater than or equal to 2 if and only if n at least 4. Okay. And this fact complicates the proof. Next lemma is about eigenvalue 1. For any odd n at least 7, this partition corresponds to the eigenvalue 1 of Tn, and for any even n at least 14, this partition corresponds to the eigenvalue 1 of Tn. And the proof of this lemma is very similar to the proof of lemma 1, and now we will not waste time to prove it. So we can take from this lemma that if we choose some big n, then eigenvalue 1 will be the element of the spectrum. Okay. And it remains for us to get more general expressions for eigenvalues using partitions, and lemma 3 and lemma 4 will help us in this. So lemma 3, if n at least 7 is odd, the next partition corresponds to the eigenvalue lambda, where lambda from is integer and lambda from 1 to some upper bound. And it should be noted that we are writing the expression for partitions throughout the eigenvalue that we want to get. And we can take from this lemma that if we choose some big n, then numbers 1, 2, 3, and so on to some big odd n, then numbers, integer numbers 1, 2, 3, and so on to some upper bound will be an element of the spectrum. And lemma 4 is about even cases, that if n at least 14 is even, then this huge partition corresponds to the eigenvalue lambda, where lambda from 1 to some upper bound. And we can take from this lemma that if n is if we take some big n, some big even n, then numbers from 1 to some upper bound will be licensed spectrum. And the proofs of lemma 3 and lemma 4 are very similar to the proof of lemma 1, and we won't waste time to prove it too. Okay, now now we are ready to provide sketch of proof of theorem 1. What we'll do? At first, we fix an arbitrary integer k from the theorem formulation, and then we consider that then we note that 0 is element of Tn by lemma 1 because we choose some big n, and lemma 1 is about if we choose big n, then 0 is element of spectrum. Then we choose n0 such that lemma 3 and lemma 4 will hold for any m from 1 to k. Lemma 3 and lemma 4 are about if we choose some big n, then values, then the numbers from 1 to some upper bound will be an element of the spectrum. And if n at least n0 is odd, we'll use lemma 3 to show that for any m from 1 to k, m is the element of the spectrum. And then we consider even case, and if n at least n0 is even, we'll use lemma 4 to show that for any m from 1 to k, m will be an element of the spectrum. And it's complicates the proof of theorem because we prove that 0 is element of spectrum. Then we prove that if n is odd, then numbers from 1 to k will be in spectrum, and if n is even, then numbers from 1 to k will be in spectrum too. Will be the element of spectrum too. Okay, that's all about small largest eigenvalues of transposition graph, and now we'll prove theorems about the third and the fourth largest eigenvalues of the graph and of the transposition graph and their multiplicities. And at first, I'll tell you what was known about the largest eigenvalues of transposition network graph and their multiplicities. Theorem: the transposition graph Tn is an integral graph such that its largest eigenvalue is n multiplied by n minus 1 over 2 with multiplicity 1, and in second largest eigenvalue is n multiplied by n minus 3 divided 2 with multiplicity n minus 1 squared. So we can take from this lemma that we know values for for largest and for the second largest eigenvalues, and we know multiplicities for these eigenvalues. Now we want to find the third largest and the fourth largest eigenvalues with multiplicities. Okay, and now we need to use this theorem. This theorem is about how to calculate multiplicity for some eigenvalue. Multiplicity of lambda I is equal to sum by partitions which corresponds to eigenvalue lambda of this expression, where here I is equal to this huge expression, and how this expression is calculated is easier to explain with an example. For example, we have this partition 3, 2 of 5, and for this partition we construct Young table, and for any box of this table we draw hooks, and for example, for this box we draw this hook, and its length is 1, 2, 3, 4. Next, for this box we draw this hook, and the length of this hook is 1, 2. And for this box we draw this hook, and its length is 1, 2, 3. And next, to calculate I, we need to divide n factorial. N is 5 is n factorial over product of hook lengths, and it's 4.3.2 and it's equal to 5. Okay. The theorem about the third largest eigenvalue. The third largest eigenvalue of transposition graph is n-1 multiplied by n-4 over 2 with multiplicity n multiplied by n-3 over 2 squared. And to provide sketch of proof of this theorem, we need more notation. So we say that partition I1 is greater than partition I2, and we'll write that I1 is greater than I2 if eigenvalue lambda I1 corresponding to I1 is greater than an eigenvalue lambda I2 corresponding to I2. Okay, and sketch of proof of this theorem. At first, we choose the partition n-2, 2 that's corresponding to the eigenvalue lambda, eigenvalue n-1 multiplied by n-4 over 2. This value is from expression 1, which corresponds partitions with eigenvalues. So we choose this partition. This partition is corresponding to this eigenvalue, and this value is our candidate for third largest eigenvalue. And next, we'll show that n-2 is greater than any other partition except n and n-1, 1. Partition n corresponds to the largest eigenvalue, and partition n-1, 1 corresponds to the second largest eigenvalue. And if we prove this fact, it will mean that n-2, 2 corresponds to the third largest eigenvalue, and that's only one partition that corresponds to the third largest eigenvalue. And how we'll prove it? At first, we show that n-2, 2 is greater than any other partition nk if k is greater than 2, because our partition have 2 on second position. And next, we show that we show that n minus 2, 2 is greater than any other partition if any other partition of len greater than 2. Okay, and then next we'll use Hooke formula for partition n minus 2, 2 to find the multiplicity of the third largest eigenvalue. And it will complete the proof. Okay, next theorem is about the first largest eigenvalue. The first largest eigenvalue of the transposition network graph Tn and greater than 6 is n multiplied by n minus 5 over 2 with multiplicity n minus 1 multiplied by n minus 2 over 2 squared. And the proof of this theorem is very similar to the proof of theorem 2, and now we won't waste time to prove it. Okay, and some discussions in the end. So today we have shown what we know about the spectrum of transposition graph. We know that numbers 0, 1, 2, and so on to some upper bound lies in the spectrum of this graph, and also we know the first the 4 largest eigenvalue of this graph, and we know multiplicities of this eigenvalues. And now we are facing with the next challenges. First challenge is to find the multiplicities of small largest eigenvalues. It's very difficult to find it because for any small eigenvalue we have very many partitions that corresponds to this eigenvalue, and it's hard to at first it's very hard to find this partition and combine it with each other. And now I have an idea how to find the multiplicities of first largest eigenvalues. And the next challenge is getting expressions for eigenvalues that lie between the smallest and the largest eigenvalues, because now we know that that numbers from 1 to some upper bound lies in spectrum, and we know that numbers the 4 largest eigenvalues, but this territory from k to first largest eigenvalues, in this territory we don't know which numbers are eigenvalues of transposition network graph. Okay, so that's all. Thank you for your attention.
Thank you, Artem, for your talk. It was very nice. Are there any questions to the speaker?
I have.
Oh yeah, please.
Can I? It's nice talk. Did you make some computational experiment?
Yes, I take, and I take. I take. I get these huge expressions by after computation experiment where I can see this dependency between partition and eigenvalue. And also I did a computation experiment that was shown that for this small eigenvalues, there are a lot of partitions that corresponds to it, and it's very difficult to calculate it in simple form.
So no pattern. There is no pattern which you can find. Even for 0, the multiplicity is difficult.
0, 1, 2, and so on. It's easier to find pattern for largest eigenvalues, but it's difficult to find it for smallest eigenvalues.
I see. And the other question is that you have a sequencer, a consecutive sequencer, which somewhere stops, right? And do you know where it stops?
I don't understand the questions.
So you have a sequence of 0, 1, 2, it
Okay.
goes by 1 up to some point.
Okay.
You manage to prove it for k, which n depends. But do you not have an idea when it stops, this sequence?
It stops closely for.
So this your result is quite tight. The result with respect this.
No. Sure. We have this estimate for n0, and this sequence stop very closely of n0 in my computation experiments.
So probably this is tight, this result in this respect.
Maybe yes.
Okay. Thank you very much for the talk. It was nice.
Any other questions, Artem? Okay, if not, then let us thank again Artem for this very interesting talk. Thank you. And our next